OSPF, Open Shortest Path First, is a dynamic routing protocol that enables routers to share information and build a topological map of the network. In this lesson, we will dive deep into the workings of OSPF, its key components, configuration, and practical examples. By the end of this lesson, you'll be well equipped to master OSPF for the CCNA 200-301 certification and beyond. OSPF is a link-state routing protocol, distinguishing itself from distance vector protocols by its unique approach to routing decisions. Routers within an OSPF network exchange information about their directly connected links, allowing them to create a comprehensive map of the entire network. This map, known as the link state database, enables OSPF routers to calculate the shortest path to reach a destination. To enhance network efficiency and scalability, OSPF employs a hierarchical design with the concept of areas. The backbone area, designated as Area 0, acts as the central core of the OSPF network. Beyond this, additional areas, such as Area 1, Area 2, and so forth, can be established to organize and segment the network. This division of areas reduces routing traffic and optimizes the overall performance of the OSPF network. By effectively managing routing information, OSPF enhances network stability and ensures efficient data transmission throughout the interconnected network. Here are the OSPF router types. 1. Internal router. An internal router functions exclusively within a single OSPF area, possessing in-depth knowledge of the area's topology and routes. However, it remains unaware of the OSPF areas outside its designated scope. 2. Backbone router. Area border router, ABR. A backbone router, commonly known as an area border router, ABR, acts as a pivotal point connecting multiple OSPF areas. Its primary responsibility involves maintaining and facilitating the exchange of routing information among these interconnected areas. 3. Autonomous System Boundary Router, ASBR. An ASBR assumes a critical role in establishing connections between OSPF networks and external networks such as the Internet. It performs the essential task of redistributing external routes from external networks into the OSPF domain, enabling internal OSPF routers to efficiently access destinations beyond the OSPF network boundaries. In OSPF, Open Shortest Path First, routing protocol, there are two crucial data structures, the Link State Database, LSDB, and OSPF Neighbor Adjacencies. The Link State Database is maintained by each OSPF router and contains comprehensive information about the state of all the links in the network. This data allows routers to create a topology map and calculate the shortest path to reach any given destination efficiently. On the other hand, OSPF routers establish neighbor adjacencies with directly connected routers. This connection is established through the exchange of OSPF hello packets between routers. The formation of neighbor adjacencies is vital as it enables OSPF routers to share crucial routing information with one another. By exchanging this data, routers can build a detailed and up-to-date picture of the network's topology, allowing them to make informed decisions about the best paths for forwarding data packets. These OSPF data structures work in tandem to facilitate robust and efficient routing within the network. OSPF, Open Shortest Path First, offers several significant advantages that make it a preferred choice for many networks. One key advantage is its fast convergence capability, which enables OSPF to quickly adapt to changes in the network topology, reducing downtime and ensuring efficient data transmission. Additionally, OSPF demonstrates excellent scalability, efficiently managing large networks without generating excessive routing overhead that can burden the system. Another advantage of OSPF is its ability to implement load balancing effectively. By distributing traffic across multiple paths, OSPF optimizes network utilization and prevents bottlenecks, leading to improved performance and enhanced user experience. Furthermore, OSPF's support for hierarchical network designs is advantageous for complex network architectures. The protocol allows networks to be organized into logical areas, simplifying management and reducing the impact of changes within a specific area on the entire network. Overall, OSPF's combination of fast convergence, scalability, load balancing, and support for hierarchical design makes it a robust and versatile routing protocol, well suited for various network environments. In OSPF configuration, enabling OSPF on a Cisco router involves two primary steps. First, we need to activate OSPF on the router using the router OSPF command, followed by specifying a process ID. Then we define the networks that will participate in OSPF by using the network command with the appropriate network address, wildcard mask, and area ID. For example, to enable OSPF with process ID 1 and include the network 192, 168.1, 024 in area 0, we would use the commands router OSPF 1-inch and network 192.168.1.00.0.0.255 area 0. Additionally, OSPF routers require unique router IDs to identify themselves within the OSPF domain. By default, the highest IP address of any active interface becomes the router ID. However, we can manually set the router ID using the router ID command, followed by the desired router ID. For instance, router ID 1.1.1.1 sets the router ID to 1.1.1.1. The provided show commands are useful tools for verifying and troubleshooting OSPF, Open Shortest Path First, configurations on a Cisco router. The Show IP Protocols command presents detailed information about the OSPF process running on the router, including its process ID, timers, router ID, and networks that OSPF is advertising. Show IP OSPF Neighbors displays a list of neighboring routers that are part of the same OSPF area, allowing administrators to check if OSPF adjacencies are correctly formed. The Show IP OSPF Interface command provides specific information about each interface's OSPF settings, such as the interface IP address, area ID, state, and cost. Lastly, Show IP Route helps in verifying the OSPF learned routes present in the routing table, offering insights into the paths the router is currently using to reach different destinations. These show commands play a vital role in diagnosing OSPF-related issues and monitoring the OSPF network's status and performance. In the practical implementation of OSPF using Packet Tracer, we follow a series of steps to set up and confirm the OSPF configuration in the network. First, we create the network topology by placing routers and connecting networks in a straightforward layout. After ensuring all routers are powered on, we proceed to step 2, where we assign IP addresses to the interfaces of each router according to the topology. This enables communication between the routers and networks. Moving on to step 3, we enable OSPF on each router by applying the appropriate commands discussed earlier, specifying the process ID and network information. This allows the routers to start exchanging OSPF-related data and forming adjacencies. Finally, in step 4, we use the show commands, such as show IP OSPF neighbors and show IP route, to verify the OSPF adjacency formation and routing table entries on each router. This verification process ensures that OSPF is functioning correctly and the routers have established communication and are using the OSPF learned routes for efficient packet forwarding. In fine-tuning OSPF configurations, one important aspect is adjusting the OSPF cost metric. The OSPF cost represents the efficiency of a link and is used to calculate the shortest path to a destination. By default, OSPF calculates the cost based on the bandwidth of the link, but sometimes we may need to manually modify the cost to influence path selection. Lower costs are preferred by OSPF when determining the shortest path. For instance, if we have 2 links between router A and router B, we can make OSPF prefer link 1 over link 2 by setting the cost of link 1 to be lower than that of link 2. In the provided example, the command IP OSPF cost 100 inches is used on the interface FA0/0 of router A to set a specific cost value, making OSPF favor this link over other links with higher costs when calculating routes. In multi-access networks like Ethernet, OSPF employs a mechanism to optimize link state flooding called the designated router (DR) and backup designated router (BDR) election. Instead of every router flooding link state information to all other routers in the network, only the DR and BDR exchange this information, reducing unnecessary traffic. The selection of the DR and BDR roles is determined based on the OSPF priority assigned to each router's interface. Routers with higher priorities have a better chance of being elected as the DR or BDR. In the given example, the command IP OSPF priority 200 inches is used on the interface FA0/0 of a router to set a specific priority value. By increasing the priority to 200, this router increases its chances of becoming the DR or BDR in the multi-access network. The DR and BDR are responsible for managing the link state information and act as the main communication points for OSPF updates within that network segment. To enhance the security of OSPF communications, the protocol offers authentication capabilities that allow routers to verify the identity of their neighboring routers. By enabling OSPF authentication, only authorized routers with the correct authentication key can participate in OSPF exchanges. In the provided example, we configure MD5 authentication on an OSPF interface. First, on the interface FA0/0 of the router, we enable message digest authentication with the command IPOSPF authentication message digest. This tells OSPF to use MD5 authentication for this specific interface. Next, we set a message digest key with the command IPOSPF message digest key 1MD5 password, where 1 inch is the key ID and password is the actual authentication password. Both neighboring routers must have the same key ID and password for authentication to succeed. By implementing this authentication method, OSPF ensures that only trusted routers with the correct authentication credentials can participate in OSPF communications, thereby enhancing the overall security of the network. One of the primary challenges encountered in OSPF implementations is the failure to establish OSPF neighbor adjacencies, which hinders proper communication and route exchange between routers. To address this issue, several factors must be verified for correctness. Firstly, it is crucial to ensure that IP addressing and subnet masks are accurately configured on all OSPF-enabled interfaces, allowing routers to communicate within the same network segment. Secondly, verifying that OSPF area IDs match on neighboring routers is essential, as OSPF adjacency is limited to routers within the same area. Thirdly, the hello and dead intervals between routers should be compatible to allow them to recognize each other as neighbors. Lastly, the OSPF network types, for example broadcast point-to-point, must be appropriately configured based on the specific link type to ensure the OSPF packets are sent correctly. Utilizing commands such as show IP OSPF neighbor and show IP OSPF interface on the router provides valuable information to diagnose and troubleshoot OSPF neighborship issues, helping network administrators identify misconfigurations or discrepancies, and facilitating the establishment of successful OSPF neighbor adjacencies. In OSPF implementations, encountering routing issues where OSPF learned routes do not appear in the routing table is a common concern. To address this, several key aspects need to be examined. Firstly, it is essential to verify the OSPF configurations on all routers, including the process ID, networks, and areas, to ensure they are correctly set up and aligned. Secondly, it is crucial to confirm that OSPF is enabled on the appropriate interfaces that should participate in OSPF routing. Incorrectly enabled or disabled interfaces can lead to missing routes in the routing table. Finally, checking for any filtering mechanisms like route maps or distribute lists is vital, as they may prevent certain routes from being advertised or received. These filters could be unintentionally blocking OSPF route updates. Using the command show IP route OSPF on the router provides a comprehensive view of OSPF learned routes, assisting in identifying and resolving OSPF routing issues efficiently. In OSPF deployments, encountering area mismatch issues is a common challenge that needs to be addressed for proper communication and routing within the OSPF domain. When routers belong to different OSPF areas, it is essential to ensure that a suitable connection exists between these areas through area border routers, ABRs. ABRs play a crucial role in interconnecting OSPF areas and enabling route propagation between them. By using commands such as show IP OSPF database and show IP OSPF border routers on the router, network administrators can inspect the OSPF database and identify the ABRs responsible for connecting different areas. Verifying the presence and correct configuration of ABRs allows for the resolution of OSPF area mismatch issues, ensuring seamless exchange of routing information and efficient packet forwarding across the OSPF network. In OSPF environments, authentication failures can impede the establishment of OSPF neighbor adjacencies, resulting in communication breakdowns. To resolve such issues, it is crucial to thoroughly verify the authentication settings. Administrators should ensure that the authentication keys match between the neighboring routers. Mismatches in authentication keys will prevent the routers from authenticating each other, leading to failed neighbor adjacencies. Using commands like show IP OSPF interface and show IP OSPF neighbor on the router provides valuable information to diagnose authentication-related problems and identify any inconsistencies in the authentication keys. By rectifying these mismatches and ensuring the correct authentication settings, OSPF neighbors can authenticate each other successfully, enabling the formation of OSPF adjacencies and facilitating seamless communication within the OSPF network. We hope this video helped you on your journey towards becoming a cybersecurity expert. Remember to subscribe to our channel and turn on notifications so you never miss out on our latest content. And if you found our videos helpful, please give us a thumbs up and share them with your friends and colleagues. Don't forget to check out the links and description for our Anki flashcards and to donate to St. Jude Children's Research Hospital. Your support can make a real difference in the lives of those in need. Thanks again for watching, and we'll see you in the next video.